Hi and welcome to Module 8, Analysis of Chemical Ideas, and we're looking today at video 2 and introducing the instrumental analysis of the organic substances. So what instruments are we using to be able to analyze these substances? And today, the topic of today's video is mass spectrometry. So looking at our outcome that is on our syllabus, and it says investigate the processes used to analyze the structure of simple organic compounds, addressing the course including but not limited to proton and carbon-13 NMR, mass spectrometry, which is the content of today's video, and infrared spectroscopy. So we'll get started and looking first of all at electromagnetic radiation. So in Year 9 you did look at the electromagnetic spectrum and looking at all the different types of radio waves, the type of light waves that we have. So we have our visible waves that fall into the region that we can see, and then we have all our other types of electromagnetic radiation that we can't see but is still there and has a variety of different purposes. So all our types of spectroscopy that we're going to be using use the electromagnetic radiation to discover that information about the different materials that we have around us. Now, when we're looking at the electromagnetic spectrum, the radiation there interacts with the atoms and the molecules that we have, and how they interact will depend on the energy of the radiation. So if we have a look at the electromagnetic spectrum here, you can see that the electromagnetic spectrum is divided into different types of radiation that we have with different frequencies, wavelengths, energies, and so forth. We would have touched on this a little bit when we were looking at radiation in our Year 11 course as well. So you can see here that our UV rays are sitting just here. So they're relatively short. We then move into our infrared, gradually a little bit bigger, moving all the way up into here into our radio waves, which are bigger again. This tiny little gap between UV and infrared is our visible spectrum, so that spectrum that we can see, and you can see there that it's broken up into the colors of the rainbow, which is what happens when white light is split by a prism. So we can see down in the gamma ray region, we can see that the waves are quite small, and so because they're quite small, their frequency is quite high. So the way they measure frequency is how many full waves will go past in a second. So obviously the smaller the wavelength, the more waves will go past, and inversely the radio waves have got really large wavelengths, sometimes up to kilometers, and so obviously their frequency is going to be lower. So what techniques are we going to have? And already I can see here there's a mistake in our video. So each instrument that we actually use, and you've already seen some of those in our visit to the TAFE, each of them will provide different information, and no one of them provides a perfect picture, and so often they are used together to give a really big sort of holistic view of the substance that we might have. So looking at these types underneath, here is a real general summary. So our mass spec that we're going to be looking at first is actually not using that spectrum there, but it's rather looking at higher energy electrons. And we're going to be looking at the ratio between mass and charge, and we'll talk about that in a minute. Then we've got NMR, that's actually using our radio waves. IR spec is using our infrared, and the UV vis spectrophotometry is using UV visible rays there. So let's get into mass spectrometry. Now, it is one of the most commonly used tools that we have, and it can be used to measure or analyze samples of solids, liquids, or gases. So it's quite handy, and it's quite a sensitive technique that we have, and it can really measure some concentrations as low as parts per trillion. So we've talked about parts per million earlier in this, or in our last unit when we were talking about polymers. Parts per million So that was milligrams per kilogram or milligrams per litre. So that's in per million. Now scale that out to parts per billion and parts per trillion. It can detect quite small quantities there. So it can tell the chemist a lot about the structure it has. And the great thing is it can tell its molar mass, which helps us work out what the structure is, and any of the isotopes that might be there as well. So it's got some great uses, detecting drugs in sporting supplements, radioactive dating of fossils, even analysing the atmosphere and what is in our atmosphere there. So let's have a look at the machine that we've got. So this is just a really simplified version. Again, you may have seen this at ANSTO when we went visiting and had a look at the mass spectrometer that they did have there. So here is our machine that we have. Now you can see here a vaporized sample is put into this machine, and that is ionized there. And that particle then, or those atoms, are accelerated, and it goes through here through an electromagnet, a quite strong electromagnet there. And what's happened is beams of ions will come in and it'll be focusing, and you can see the different paths that ion might take. So beams of ions will be focused in different strengths. What will happen is we'll come out here, it'll be detected, amplified and recorded on a chart. So let's look at those steps a little bit closer. So what's going to happen is we've got the ions are formed in the ionization chamber. So that's when the sample is exposed then to high voltages there. And when it's exposed to those high voltages, electrons are being knocked off that molecule, and what happens then is we form a molecular ion, which is or the parent ion, which will then have a positive charge because one electron has been knocked off. And then the ions are separated in that magnetic field, and it's separated on a basis of a ratio, which is their mass to charge, and that's shown by the MZ, M being mass, Z being charge. And so what's happening is the detector actually detects those, how many ions have that different charge, and so it'll be shown in a mass spectrum, and the intensity of that each fragment will be measured. So having a look just here, we can see what we mean about that intensity and what's actually happening in that electromagnet here. So you can see here, if we're talking about the electromagnet, in this one here, the electrons are kind of too heavy to be properly deflected, so they're too large, so they are just being removed by the vacuum pump. These ones up here, they're so small that they're almost deflected too much, and they kind of go off the chart a little bit, and they're also removed by the vacuum pump. But these ones here are the ones that actually reach the detector and will produce the peaks. So you can see here lots of different peaks and of their relative intensity. So this one here would be our base peak, and we give that height of that peak a relative intensity of 100. So that's what we compare all the others to in regard to their intensity. So the greater proportion of those ions in that sample, the higher that peak will actually be. So how do we interpret a mass spec? So what features are we going to see first of all? So looking at this example here, we've got an example of pentane. So what we're seeing is the abundance, relative intensity, and the different mass to charge ratio. So you can see over here, as I said before, we've got pentane. Here's its formula given. Pentane, and this is our molecular ion. One electron has been knocked off, so that gives our ion a positive charge. That also gives us the mass of the substance. Although we've lost one electron, electrons don't have a great deal of mass, so the mass here is still the same of the molecule that we started with. So that's really good that we can use that mass to try and help work out what the substance is, also based on the other things that we've got in our spectrum. So we can see here we've got a base peak at 43. So we'll talk about how we read this in a minute, but it's more than likely that what we have got, a CH3, CH2, CH2, so a CH3, CH2, CH2, that we have lost here a CH2 and a CH3 from that parent to this big peak here. Again, set 57 to 72 is a difference of 15, so that'll be the loss of a CH3. So the bonds have been broken and a CH3 has been removed. Again, we'll talk about that with these features on this example here. So as I've said already, 72 is our molecular ion, sometimes known as parent ion. It's important to know both, just in case different people use different things. So as I said before, it gives the mass. So let's look here again. Other peaks, we've talked about the base peak that is there. It's the most abundant. It's assigned a relative intensity of 100. So what's happening is high energy electrons are causing bonds to break, and so they're just breaking into their different fragments. So some really good things to remember. You can work these out yourself. It's not difficult to do so, but certainly if you start to remember some of the patterns of numbers, it certainly helps a lot there. So these can help provide clues to the structure of the molecule, and the fragments are produced by breaking almost any bond in the molecular ion, and that can be atoms, groups of atoms, or even large sections of the molecule. And if we find that the difference between the parent ion and one of the other peaks is 15, it's more than likely that a CH3 has been knocked off there. If the difference is 17, it's likely to have lost an OH. Again, 29, 31, 35, and 37, when we have peaks there, they are often our chlorine atoms. 45 is your COOH. So you can see how we can start to form a picture, and you'll see that even more so as we do some examples. So let's have a look. So here we have got the mass spectrum of ethanoic acid. So we're all familiar with ethanoic acid. And we can see over here we have got CH3 COOH plus. So that's that one electron that has been lost there. So that is our molecular ion. That also gives us our mass. So the mass of ethanoic acid is 60. So we can now see our next peak is 15 down at 45. So you can see there that that's a loss of 15. And when we talked about 15 on the previous slide, that correlates to CH3. So CH3 has been removed, and what's left behind is a COOH. And as you can see, they have marked that there on this graph. If you look over here, you can also see over here a molecular ion of MZ ratio is 60. A loss of a CH3 will bring our MZ down to 45, and now we're left just with that COOH. It does help to sometimes draw some diagrams to help you build the picture. So here I have again my molecular ion. On our previous slide, we saw that 17 corresponds with the OH. So we can see here from our initial one, knocking off there the OH, or breaking it into the fragments, an OH has been lost. So if we lose an OH from this structure, imagine if we move that, we're left with CH3C double bonded to the O, and we can see that in the molecular structure there. If I just lost the COOH, we would just be left with a CH3, which would be this peak down here at 15. Again, from this 43 peak, we have got a very close peak only at 42, and that would correspond to a loss of an extra hydrogen. So we're constantly breaking it into fragments as we go. So let's have a look at an example here. So the mass spectrum shows an unknown substance, and chemical testing has identified the compound as an alkane. So we know there's only single bonds there. We know it's just carbon and hydrogens. We need to identify what the alkane is, and then we need to account for the different peaks at 15, 28, 29, and 43. So we do know by looking down here, 40, 41, 42, 43, 44. So we have a mass of 44. So we know that's our parent molecular ion. Yes, it's positive charge, but the electrons don't have that mass. So our mass is 44. Using our general formula of alkanes, so CnH2n plus 2, we should be able to work out then what our general formula for this substance is. So pause the video, have a bit of a play with the alkane general formula and see if you can come up with what alkane will give you a mass of 44. Okay, hopefully you have had a bit of a go and worked out that the substance is propane. So CH3, CH2, CH3. So the peak then we've got at, what have we got? Let's have a look. We have got 43. So that will be a loss of a molecular ion. So we have got that as our molecular ion there. A peak at 29. So 29 plus 15 brings us up to that 44, which is our mass of our substance. So there's a loss of a CH3 group. So then that is leaving us with the CH3 and CH2 remaining. A peak at 28 is an extra loss of a hydrogen there. So that would bring me back to a CH2, and our peak at 15 is a CH3 ion on its own, so therefore we've lost the CH3, CH2. So let's have a look at this in a different tabular form, which is what I meant when I said sometimes it might be better if we have a look in a visual form. So we've got our parent molecular ion here. Here we've lost one hydrogen. So now we have got CH3. What have we got? CH3, CH3. So that's that loss there. Here again, starting from our parent molecular ion, if we lose a CH2, CH3, we'll be just left with the CH3, which has an MZ ratio of 15. And on this side here at 29, we've lost the CH3 and we're left with the other component there, which is 29. And again, 29 to 28 is a loss of a hydrogen atom. So we're going to try and just break it down. More and more practice will certainly make perfect, and we'll work on this together because, of course, this new syllabus, it's a little bit new to all of us. Have a go at this question, and I would like you to come to class with your answers done. So here we have a mass spectrum of hexane showing some peaks that we've got there at 15, 29, 41, 43, and 57. So have a look. It's telling you already it's hexane. Write out your structural formula of hexane. Draw some diagrams like what we're seeing in this one here to help you break it down. So see if you can identify any possible fragments there in that diagram. Actually, looking at that, no, it's talking about having a mass spec and it's giving you the peaks. Have a look at those and see if you can work that out. In the second diagram, it's the figure there is showing you the mass spectrum of 3-pentanol. So again, account for the peaks at 31, 41, and 59. And they've given you a little hint there saying we're not working from the molecular or parent ion to work out 31 and 41. It's actually due to further fragmenting of that ion that you've got at 59. Now, 1-pentanol has some peaks at 31 and 57, but none at 59. Have a bit of a think about why you think that might be, and we'll discuss it in class tomorrow. Don't forget, use your notes from our visit to TAFE. There's some extra notes there to complement what we have in today's video, and some pictures and diagrams that might help you a little bit further, and we'll discuss these further in class tomorrow. See you then.